Hey guys, Dr. Brown here, and tonight we're going to talk about 8 tools to master calculus integration. If you follow the channel, you know I talk about UTI, PPLCQ. We're going to go through each one of those, the U-Sub, Trig Sub, integration by parts, partial fractions, power reduction, long division, completing the square, and something I call method of quadratics. So if you can master these, you can kick butt in Calculus 2 or the integration of calculus. So let's get after it, okay? So the first one we'll look at is U-Sub. You will use that over and over and over again. It's a handy tool. So how does it work? Okay, we have the integral of x over 1 plus x squared dx. Okay, now there's several ways to solve this one, but we're looking at U-Sub. So let's let U equal 1 plus x squared. Du, or the derivative of U, derivative of a constant is 0, derivative of x squared is 2x dx. Now, ultimately, we're trying to get from the x world to the u world, so everything would have to be some function of u. So I need to solve for dx. I'll divide both sides by 2x. So du over 2x equals dx. So now let's fill in the blanks here. We have the x, we still have that at the moment, over 1 plus x squared, which we said was u. And then dx is du over 2x. The x's cancel. Hey, I'm going to take the 1/2 to the outside. So I have 1/2 the integral of du over u. And we know the derivative of a function over the function is natural log of that function. So I have 1/2 natural log of u, but u is 1 plus x squared plus c. And that is how the U-Sub would work. Let me think offhand what might be another. Let's say, what if we have I don't know, what if we had e to the, let's see, x squared e to the x cubed dx. We know the integral of e to the u du is e to the u. So if I said u equals x cubed, du equal 3x squared dx. So du over 3x squared equals dx. So now fill in the blank again. X squared e to the u, and dx is 1/3. I'll put it to the outside. Du over x squared. So bad too. Those cancel, so I have 1/3 the integral of eu du, which is 1/3 e to the u, or 1/3 e to the x cubed plus c. That's how U-Sub works. It is a powerful tool. As we discuss some of the other tools, we'll have to use a U-Sub within that tool. So it gets used often. All right, that's U-Sub. Our next tool is Trig Sub. Okay, we have the integral of x over 4 plus x squared dx. Now, when you're looking at a problem, actually the one we had earlier when I said there's several ways to solve that, we could have used Trig Sub on it, but I wanted to use it for U-Sub. When you think about trig identities, 1 minus sine squared equals cosine squared. Let's say 1 plus tangent squared x equals secant squared x, or secant squared x minus 1 equals tangent squared x. So when you look at this, I have, and I can think about 1 squared plus tangent squared. I have something squared plus something else squared. 2 squared plus x squared. So when I look at that, I say, oh, hey, I can use a tangent function for that. So I'll let a squared equal 4. A equals 2. X equals a tangent theta. Dx, the derivative of that, the constant multiple rule, we can pull, we're taking derivative of a function, we can pull the constant out and then take the derivative of that. So I have a times the derivative of tangent, which is secant squared theta, now chain rule, d theta. Okay, so I have the integral of x, which is a tangent theta, over a squared plus a, this was x squared, so that's a squared tangent squared theta. And then dx was a secant squared theta d theta. So now we've gone from the x world to the theta world. And all the x's are gone. Let's see. Let me take a times a, that's a squared. I'll get rid of those. I'll factor out an a squared here. I'll factor that out. So that would be 1 plus tangent squared. Oh, 1 plus tangent squared. What is that? Secant squared. Secant squared divided by secant squared. Those cancel. A squared is canceled. What do I have left? The integral of tangent theta d theta. Now, certain things you need to remember because it'll happen a lot. We should be able to look at that and say, wow, that's minus natural log cosine theta. But if you can't do that, that's okay. Okay, because we know tangent is sine theta over cosine theta, d theta. Now we can use the tool we just learned, a U-sub. We could say U equals cosine theta. Du equals, the derivative of cosine is minus sine theta d theta. So du over minus sine theta equals d theta. Because I've got to replace it here. So now I have the integral of sine theta, the sine I had, divided by cosine, which is u, and du over negative sine, du over negative sine theta. Sines cancel. I have minus the integral of du over u. So that's minus natural log u. And that equals minus natural log u is cosine theta plus c. That would be this guy here. The integral of tangent is minus natural log cosine theta. Oh, but we're in the theta world. Minus natural log cosine theta. Where were we? We said x over a is tangent theta. If I divide both sides by a, x over a equals tangent theta. So my triangle, theta, x over a, and a was 2. So this would be 2 squared plus x squared. So 2 squared is 4 plus x squared. Hey, that looks familiar. Okay, so now minus natural log of cosine, which is adjacent over hypotenuse. So that's 2 divided by square root of 4 plus x squared. Now plus c. Now we're back to the X world, which is where we should be. That is trig sub, okay? Now, integration by parts. Hopefully you've heard about the DI method. When I learned integration by parts, we learned it the old school way. That reminds me, a guy the other day said, "Man, you look 70 years old." I didn't realize math was just for young people, but I told him it must be the lighting. I don't know. I'm not 70, I'm 67. Thank you very much. Okay, and all I'm trying to do now is pass along something to help you. Okay, I'm retired, so I'm beyond help, I guess, but I love sharing math that made a difference in my life. It took me out of the hog barn and put me in the National Academy of Sciences one time. So math is powerful. Learn it, use it, expand your mind. Okay, let's expand on some integration by parts. What if we have the integral of x squared sine x dx? Okay, integration by parts says I have two pieces to this thing. Which piece can I integrate? In this case, I could integrate both of them. So, but since I know the DI method, you know, when you use the old school integration by parts, you start out here, the next time you're subtracting, next time you're adding. So just put that in the table, okay? And remember, you have U and dV. That's what these two columns are for. What am I going to differentiate? What am I going to integrate? So I'm going to pick x squared as this term that I'm going to differentiate, and sine x dx, what I'm going to integrate, okay? Now, with the DI method, there's three stops. Well, let me back up. With the old school method, there wasn't a stop. I mean, you could just, well, it wasn't something defined as a stop. So in the textbooks, they would say, okay, just do this through 2 iterations, or do it to three different steps. This one, you can get the full equation. Now, you could with the other, you just didn't know what the stops were. But this one, if you differentiate, you know, you're going row by row, and you get down to where the derivative is 0, that's the stop, because you're integrating that last row wherever you stop, and 0 times something there, I just end up with a constant of integration. Okay, that's one stop, end up with 0. The second stop would be, if I get to a row that I can integrate that row, then I can stop and just finish out the table by integrating that row. The last stop would be if it starts repeating itself. There's certain functions you'll go along and you'll end up right back with what you started with. Now, there may be some coefficients out here, but you'll see these same terms again, and that's when you stop. Go ahead and integrate, because most likely if it's repeating, then your original function you can subtract out, or you can do some things with it and solve. Okay, so let's do this one. All right, what's the derivative of x squared? It's 2x. What's the derivative of 2x? It's 2. What's the derivative of 2? 0. Hey, what does that mean? I'm going to fill in the rest of this and stop. Okay, what's the integral of sine x? Well, the derivative is cosine. The integral is minus cosine x. Okay, if I integrate, the derivative of cosine is minus sine. The integral is positive sine, but I have that negative, so it's still negative sine x. Now the integral of sine is minus cosine times that negative gives me a positive cosine x. Now u-v, with the old school way. Okay, so what do I have? All the signs you need are right here. Positive times negative. I have a negative x squared cosine x. Negative times negative is a positive, so 2x sine x. And positive times positive is positive, so 2 cosine x. How easy was that? Now, I would encourage you, let's say I have some big equation here, and I end up with minus this. I would encourage you to do that and put that negative, the sign, all the signs of what you need, put them right there. Now that negative would follow me along if I did that. And I wouldn't have to remember, I wouldn't have to remember that I had a negative out here. That's what used to trip me up with the old method. Okay, so that is integration by parts. Recall, 3 stops. You take the derivative, you get down to 0. That's the last of what you do. Oh, and by the way, we integrated that row, but it's 0. Okay, there's my C. So wherever you stop, you have to integrate that last row. So 3 stops. Get a 0, that's where I stop. If I see a row I can integrate, I stop there. If it repeats itself, that's a stop. Go to black pen, red pen, to this guy on YouTube. The guy is phenomenal. Look for his DI explanation. He does a fabulous job with that. Okay? So that's integration by parts. Okay, our next one, partial fractions. This is everyone's favorite right here. Whoa. All right, partial fractions. Let's say we have the integral of 5x plus 2 over x squared minus x minus 2 dx. If I have something I can factor into some items that make sense, it's, in this case, I have 5x plus 2 over x minus 2, x plus 1 dx. So x squared minus 2x plus 1x, minus x minus 2. Okay. Partial fraction says, and by the way, there's linear, linear repeated, quadratic, and quadratic repeated. There's 4 different forms that you can use to solve. This one's a linear, so I have some linear terms here. So partial fraction says I'm going to break the whole thing into partial fractions, thus the name. So a over x minus 2 plus b over x plus 1, all integrated with respect to x. Now, if I were to multiply through both sides by x minus 2, x plus 1, it cancels here, and I'm left with 5x plus 2. If I do that on the other side, I'm left with a, I'd have x minus 2, x plus 1. The x minus 2's cancel. I'm left with x plus 1 plus b, x minus 2. The goal is to solve for a and b and plug them back up here and go through the integration. And you just guess a number, not just any number. For example, if I let x equal negative 1, this will go to 0 and I'm left with just one term. Hey. So negative 1 times 5 is negative 5 plus 2 is negative 3 equals negative 1 plus 1 is 0. So all of this is 0 plus negative 1 minus 2 is negative 3. So that's minus 3b. So if I divide both sides by negative 3, I get b equals 1. Okay, so b is 1. Let's go through this same thing again here. If I let x equal 2, 5 times 2 is 10. 10 plus 2 is 12. Okay. And then, where do we go? This is 0. So 2 plus 1 is 3. So 3a equals 12. 12 over 3 is 4. And that equals a. So let's plug those in. I have a 4 and I have a 1. Okay. So 3, 2, 1. I'm going to erase this. All right. I like to break things into multiple integrals. So I have the integral of 4, bring that to the outside, over dx over x minus 2 plus the integral of 1 dx over x plus 1. Now, if I were to go to u sub and say, well, u equals x minus 2, and eventually you'll go, oh, that's 4 natural log x minus 2 plus natural log x plus 1. But back when I first started this, I couldn't look at that and tell that, okay? So maybe some of you guys struggle with that also. That's okay. So let's let u equal x minus 2. du equals dx. Wow, because the derivative of x is dx, derivative of a constant is 0. So I have 4 times the integral of x minus 2, which is u, dx, which is du. The integral of du over u is natural log u. So I have 4 natural log of u. I'll just go ahead and write it. That's equal 4 natural log of x minus 2. Okay, let's look at the other one. The other one, same concept, right? X plus 1, so this would be plus natural log x plus 1 plus c. Okay, that's how you use linear partial fractions. What if it were linear repeated? And by that I mean, oops, I need to keep that, x plus 2 over, what if it's x minus 2 x plus 1 squared dx. So I have a linear term, but now I have a linear term repeated. So it's the integral of a over this first linear term plus b over, now you're going to repeat that term for up to the n powers. So I'm going to say x plus 1 plus c over x plus 1 squared dx. Go through the same scenario. I'm going to multiply all of this times this side times every term there, and whatever cancels. Now I have this big long equation. I'm going to solve for a, b, and c. What if it's quadratic? I mean, you guys understand what I just said, right? If I multiply this by x minus 2 x plus 1 squared, they cancel on this side. So now I've got a over x minus 2, and I'm multiplying it by x minus 2 x plus 1 squared. Well, the x minus 2 cancels, so this would give me a x plus 1 squared. Okay, so now I'm doing that plus b over x plus 1 times x minus 2 x plus 1 squared, which is x plus 1 times x plus 1, right? Okay, so one of those cancels, so I'm left with b times x minus 2 times x plus 1. I repeat that for c. I'm running out of space. So I have c over x plus 1 squared, and I'm multiplying x minus 2 times x plus 1 squared. Okay, this and this cancel, so I'm left with c times x minus 2. And that equals 5x plus 2. You're going through the same scenario again. If I let x equal -1, that cancels out. That cancels out, and I can solve for c. And you just repeat that. You may end up with a system of equations, you know, a matrix that you have to solve. All right, so that was linear repeated. What if I have a quadratic? What if I have x squared plus 4? Let's do a linear and a quadratic. I have x times x squared plus 4. So I have, for the linear term, a over x plus bx plus c over x squared plus 4. That would be the form I have to use for that quadratic, dx. Now, if it's a quadratic repeated, I have that scenario. I have to, just like I did earlier, if it's repeated, I have this to the first power plus dx plus e over x squared plus 4 squared dx. That's how to handle the repeated. So the method for repeated is the same. It's different about what you have to put on the top that is of the same similar form as a quadratic. Okay, that's partial fractions. They're super helpful. When they get this large, try to look for a different way to solve that. Okay. All right, power reduction. This comes in handy. How do you integrate cosine squared x dx? Now somebody might say, well, that's 1 minus sine squared. That's true. That's a trig fact. Now how do you integrate 1 minus sine squared? How do you integrate that sine squared term? Okay, in this case, I utilize a trig identity that's a power reduction, because cosine squared is 1/2 times 1 plus cosine 2x dx. So this 1/2 1 plus cosine 2x, that is cosine squared. Okay, and I can break that apart. I can distribute that dx and the 1/2 to the inside, so that's 1/2 dx plus the integral of cosine 2x dx. Well, the integral of dx is x, so I have 1/2 x plus the integral of cosine 2x. Well, u sub, hey, u equals 2x. du equals 2 dx, du over 2 equals dx. So the integral of cosine u du over 2. So I'm going to move the 1/2 outside. Okay, so what do we have here? Oh, by the way, you see this big crack in my board? We just step over it. Life is that way. You're going to come along with things in life that just cracks that impede your life. Just step over it, move on, keep going. I used to tell my kids, even if you fall down and you fall forward, it's still progress. Rock on, okay? All right, so we have 1/2 x plus 1/2 y. What's the integral of cosine u? It's positive sine u. So, but what is u? U is 2x. Now then, there's another trig identity out there. It says the sine of 2x equal 2 sine x cosine x. So I'm going to change that. So I have 1/2 x plus 1/2 times 2 sine x cosine x. Oh, sorry, made a mistake here. Du over 2. We had a 1, here's my mistake. That 1/2 should have gotten distributed in here also. So I already had a 1/2. And then du over 2, that would have made this a 1/4. Hopefully somebody noticed that and you were screaming into the video. All right, so that's 1/4. Sorry for that. All right, so now we have 1/4 times 2 sine x cosine x. So that's 1/2 x plus 1/2 sine x cosine x plus c. Actually, this is why I break it into two integrations or integrals, such that I don't make that mistake, and then I made it anyway. That's a kryptonite for me, okay? You'll see things that I do to try to prevent that, and muffed it. Okay, so that is power reduction. Now, if you were trying, let's say we had that integral earlier, integral of sine squared that we just mentioned. Well, that is 1/2 1 minus cosine 2x dx. So that is the trig identity for that one. Powerful tool, power reduction. That falls into power reduction associated with long division, our next tool. I was coaching a college group, and we had some equations. I said, wow, let's just do long division on that. And I guess with the advent of calculators, maybe they had forgotten how to do it. So I put it in as a tool because it really helps. Let's say I have x minus 2 over x plus 1 dx. How do you integrate that? Well, I don't know. So what I do when I look at something like that, if I can't factor anything out, that's one of my rules, when in doubt, factor. So I'll just go ahead, well, it's divided, I'll just go ahead and divide it. X will go into x one time x is x, 1 times 1 is 1. Now what am I trying to do? I'm trying to subtract that parentheses. So I put a parentheses around it, put a negative out here. X minus x, 0. Negative 2 minus 1 is a negative, minus 1 is a negative 3, okay? So I end up with the integral of 1 minus 3 over x plus 1. Well, it totally changes the whole concept here. So I have, let's break it apart and not mess it up this time, integral of 1 dx minus 3 integral of dx over x plus 1. So this integral of dx is x minus 3. Oh, what is this? Natural log x plus 1. We just did those earlier. Long division greatly simplifies things, but there's a few rules that go along with that. Okay, let's look at a few of those. What if I have x squared plus 4 divided by x cubed plus 3x minus 5? Can I do that? No. One of the rules for long division using these is the fact that the power in the numerator needs to be equal to or greater than the power in the denominator. Okay? That's one of the rules. Don't get caught on that. Another rule would be if I have, let's say, x plus 1. X squared minus 2x. Okay, let's see what this works out to be. The other rule would be let's just do it this way. I have a squared term, but I don't have x to the first power. So I need to rewrite this. Here's my 4. Like that. I need every power of x in there, but if there's not one in my original equation, just put a 0 in front of it. And you're going to see why in just a moment. Okay, x squared goes into x squared one time. 1 times x squared is x squared. 1 times 2 is 2. That's not a good example. Let's put my x back here. Okay, 1 times 2x is 2x. There we go. So 1 times x squared is x squared. 1 times 2x is 2x. You see, I needed the placeholder for the x because what am I doing with that? Parentheses, subtract. X squared minus x squared is 0. 0x minus 2x is minus 2x. Bring down the 4. Okay, so now I can't keep going, but I would have 1 minus 2x plus 4 over x squared plus 2x, which is 1 minus 2x plus 4 over x times x plus 2. So I'm integrating that. Hey, check that out. I could do a partial fraction on that piece of it, couldn't I? But that's long division. Okay. Completing the square. I have the integral of x over x squared plus 6x plus 13 dx. Taking the integral of that with respect to x. Can I factor this? If I maybe could factor it into something okay, I might do a partial fraction. But I cannot. So I'll take this term, move it over here, x squared plus 6x plus something minus something plus 13. I'll put a parentheses right there. Now, you know the ax squared plus bx plus c, that's quadratic form, a, b, and c. The b term, we're going to take b divided by 2 and square it. Whatever that comes out to be, that's what I'm putting in that box. And if I add it in that box, I have to subtract it in that box. So what do we have? 6 over 2 is 3. 3 and square that, that's 9. So I'm going to add 9, subtract 9. Man, we are rocking now. Now, I take the square root of the first and last term. So the square root of x squared is x, square root of 9 is 3. Whatever the sign is here, that's the sign I put there. Put a parentheses around that square. 13 minus 9 is 4. It's a positive 4. That's 2 squared. So this x squared plus 6x plus 13, I've turned it into the sum of 2 squares. Let's FOIL this and make certain we're okay. So x plus 3 squared plus 4. So that's x squared plus 3x plus 3x, that's 6x plus 9 plus 4. Hey, that's 13. So x squared plus 6x plus 13. So we know that's correct. All right, so we've transformed our equation into x plus 3 squared plus 2 squared dx. But we're not finished. What are we going to do with that? Recall what we said earlier. We have something squared plus something squared. That looks like tangent squared plus 1 squared. Let's do that. Let's try that. Okay, so this would be my a squared term. So a squared equals 4, a equals 2. So x plus 3 equals a tangent theta. So if I take the derivative of both sides, dx equals a secant squared theta d theta. Well, we have an x term up here. Well, let's keep going. You'll see what I mean. So x plus 3 squared, that's a squared tangent squared theta plus a squared. We have a dx, we still have that x. We have dx, which was a secant squared theta d theta. X, if I solve for x in this equation, x equals a tangent theta minus 3. I subtract 3 from both sides. So let's replace that x with a tangent theta minus 3. Okay? Well, let's factor this a square out down here. So I'm going to put parentheses there. So if I distribute that, that's a squared tangent squared theta plus a squared. Okay? Now I can take that a squared and this one, that gives me 1 over a. Tangent squared theta plus 1 is secant squared. Secant squared and secant squared, those cancel. I'm left with 1 over a. We're stepping over the line in life, okay? That is the integral of a tangent theta minus 3 d theta. Is that correct? I think we're good. All right, let's distribute the 1 over a into the inside here. So that will cancel this one. So that's the integral of tangent theta minus 3 over a integral d theta. So we saw earlier that the integral of tangent was minus natural log cosine theta minus 3 over a theta. Let's go up here. All right, what did we have? We draw our triangle. Put theta in that corner. So x plus 3 over a was tangent. So the opposite over the adjacent, and a was 2. So that gives me a squared plus x plus 3 squared. So a squared, which is 4, 4 plus x plus 3 squared. And we know this to be x squared plus 6x plus 13. We know that. All right, so I have minus natural log of cosine, which is adjacent over hypotenuse. So 2 over the square root of x squared plus 6x plus 13 minus 3 over a, and a was 2, theta, which is tangent inverse x plus 3 over a. Oh, and a is 2 plus c. that correct? I do keep the answers over here just in case. Sorry for the mess. Looks a little disorganized. That's completing the square, okay? Now, this other one's method of quadratics. That's just a name I've coined. I needed an acronym. So it's just a matter of taking and separating out terms. Let's see, what do we have? We have 5x plus the integral of 5x plus 2 over that same x squared minus x minus 2 we had earlier. Well, if I take the derivative with respect to x of the denominator, what is that? 2x minus 1. Okay, but in the numerator, see, if I had 2x minus 1 over this function and I'm integrating it, I would have the natural log of that function, but I don't have that. So I think this is where just pure mathematicians do better. They'll say, well, I'm going to put that up there. So, well, you think, well, how do they do that? Okay, they do it like this. I have 5x plus 2, but I need 2x. So I need to subtract 3x from that. Well, if I subtract 3x, I need to add 3x. Okay, I need a negative 1. Well, I have a positive 2, so I need to subtract 3. Well, if I subtract 3, I need to add 3. And all of that, I'll separate it out, would be over x squared minus x minus 2. Like I said, I like to separate things out. So 5x minus 3x gives me 2x. Okay, that's 2x. 2 minus 3 gives me negative 1. 2x minus 1 is the derivative of that function over the function. So that's the natural log of x squared minus x minus 2. Okay, so we're through with that piece. What about this one? Let me factor the 3 out. That's 3 times x plus 1. And I'll factor this one is to x minus 2, x plus 1. X plus 1's cancel. So I'm left with plus the integral of 3 over dx over x minus 2. Voila. What is that? 3 natural log x minus 2. Okay. So that is what I call method of quadratics. If you can parse things out, it may make it simpler to do. Because what am I going to do with that? Well, we did partial fractions earlier. You could do that. Okay, now if you're keeping score, you may notice that with the method of quadratics, I ended up with this answer. But under partial fractions, I ended up with that one. And they look different. Okay, they look different. So let's prove that they're the same. Because I noticed they look different also. So we had in the partial fractions, that integral of 5x plus 2 over x squared minus 1, or minus x minus 2, it came out to be 4 natural log of x minus 2 plus natural log of x plus 1. Okay, we're saying that equals natural log of x squared minus x minus 2. Where'd it go? Plus 3 natural log x minus 2. I have everything right here. All right, One thing that I noticed was this, natural log. I can factor this as we've done earlier. That's x minus 2, x plus 1, plus this term that I already have, 3 natural log x minus 2. One of the rules of natural logs, if I have the product, in order to get the product, that's the sum of two natural log terms. So that equals the natural log of x minus 2 plus natural log of x plus 1 plus 3 natural log x minus 2. Okay, if I have 3 tomatoes and 1 tomato, how many tomatoes do I have? I have 3 plus 1 is 4. I have 1 natural log x minus 2 and 3 natural log x minus 2. That gives me 4 natural log of x minus 2 plus natural log x plus 1. And you'll see that's exactly what this is. So those two are the same, and that'll happen in calculus quite a bit, where you'll go through and solve a problem and the form looks a little different than this, maybe what the author has in the answers in the back of the book. Okay, all right. U-sub, trig sub, integration by parts, partial fractions, power reduction, long division, completing the square, method of quadratics. The 8 tools, if you will master these, get good at it, okay, Calculus 2 will be much easier for you and you'll kick butt in that course. Why are we doing this? Together we're trying to build a better tomorrow through math. Keep studying and we'll talk to you next time. Thanks.